All right, so on your mock test, you had 4 questions. The first one was, an AM radio station broadcasts at 1010 kilohertz and its FM partner broadcasts at 98.3 megahertz. Calculate and compare the energy of the photons emitted by these 2 radio stations. What I've done here is I've converted the frequency, in the first case, of the AM photon, 1010 kilohertz, multiplied by 1000 hertz per kilohertz gives you 1.01 million hertz. Then I entered it into the Planck equation. There's Planck's constant times the frequency gives you the energy of 1 photon. I put it to 4 significant figures. I did the same calculation for the FM photon, except now it's a megahertz, so you got to multiply by 1,000,000 to get the hertz. Plug that into the Planck equation, you get that energy per photon. I compared the energy of the 2 photons by putting the more energetic one in the numerator, and you see that the FM photon has 97 times the energy of the AM photon. In 628, a stellar object is emitting radiation at 3.55 millimeters. A, what type of electromagnetic spectrum is this radiation? I've converted it to wavelength in meters. Looked it up in the back of the book. It's a microwave photon based on the wavelength, because there was a scale in the book that you can look up. Then we plugged it into the frequency equation. So frequency times lambda times frequency gives you the speed of light. I rearranged it to solve for the frequency. There's the speed of light divided by the wavelength, and there's your frequency of your photon. I plugged it into the Planck equation to see how much energy per single photon. 5.6 times 10 to the minus 23 joules per 1 photon. We know that there are that many photons being emitted by the source per second. So per second, if you were to multiply this number by that number, you would get how much energy was emitted in 1 second, but they asked you for an hour. And we know there's 3,600 seconds in an hour, so I multiplied by 3,600 seconds. Seconds cancel, photons cancel, you're left with an answer in joules, and it comes out to 6.45 times 10 to the negative 11 joules of energy. Still a very small amount. You can understand why telescopes have to have such large objective lenses, because they have to accumulate as much light energy as possible to make an image that's worth anything. And sometimes when they don't have a large lens, what they do is they expose the camera, the film or the charge couple device that records the presence of light for hours or minutes to create a better image. You can't really do that with your eye. Your eye collects data on a per second basis instantly, so you get what you get. But our eye is a good compromise because it has good night vision and pretty good day vision and pretty clear at that. Okay, 636B, it asks, for each of the following electronic transitions in the hydrogen atom, calculate the energy, frequency, and wavelength of the associated radiation and determine whether the radiation is emitted or absorbed during the transition from N4 to N1. I asked you to do only B. So it's for N5 to N2, and I used the Balmer formula, 1 over the wavelength of the light is equal to Rydberg constant times the final condition minus initial condition squared, 1 over that is. Plugged in the numbers, so 2 squared, 5 squared gives you a quarter minus 125th. That works out to 2,304,483. We take the reciprocal of both sides to find lambda. That gives you a wavelength in meters, and I converted it to nanometers. It corresponds to a violet, probably violet or indigo photon of light. And then we found out its frequency. We know the lambda. We know the speed of light. So we isolated for frequency. Here we have frequency. I rounded it to 3 significant figures, plugged it into the Planck equation to find the energy of 1 photon of this light. You get 4.58 times 10 to the negative 19. The last part, I'll bring this one first. The last part is on the other board. Right. In 54 it asks, which of the following are permissible sets of quantum numbers for an electron in a hydrogen atom? There are 4 questions, n equals 2, L equals 1, m sub L equals 1, and several questions of the same type. So in the Schrodinger wave equation, only certain numbers can be used. So the Schrodinger wave equation was solved using the model of the vibration of a guitar string, but applying it to the standing wave that the electron was presumed to have when it was near the nucleus of the atom. And what resulted was a solution that generated geometric shapes like a lemniscate, which is a figure 8 shape, or a sphere, but only some numbers worked in the equation. If you applied certain other numbers, it would create impossible answers. So the Schrodinger wave equation, the correct answers are limited by the following parameters. The value of the principal quantum number has to be an integer value of 1, 2, or 3. The azimuthal quantum number is always 1 less or lower than the principal quantum number. The magnetic quantum number can be in between the negative and positive values of the azimuthal, and then the magnetic spin could be plus or minus 1/2. So each electron has 4 numbers representing it as the solid equation relates. So if we have n equals 2, L equals 1, and m sub L equals 1, what's possible? Well, we know that if n equals 2, L can only be 0 or 1. And if m sub L m sub L can be -1, 0, or 1, but in this particular question, you'll see in that little rectangle, they said that it's going to be only 1. They've reduced the number of possibilities to only +1. So if you follow the rules that they set for this question, it can only generate 2 possible sets of viable quantum numbers, 2, 1, 1 plus 1/2 and 2, 1, 1 -1/2. So that corresponds to a 2p orbital. How can you tell? When L equals 1, you get a p orbital. If L equals 0, it's an s orbital. If L equals 2, you get a d orbital. And if L equals 3, you get an f orbital. So it goes 0, 1, 2, 3, SPDF. Part B, they said n equals 1, L equals 0, m sub L equals -1. L can be 0 under these conditions because it's 1 less than the integer value of n, but m sub L cannot be -1 under those conditions. It can only be 0. So this is not a possible quantum state. Not a possible correct answer. Then, well, that's pretty precarious right now. Last one. Let's just lift it a little bit. Okay. So question C, it says the parameters are n equals 4, L equals 2, and m sub L equals -2. Now, if n equals 4, L can be 0, 1, 2, or 3, and m sub L can be anywhere from -3 to +3. But if they say that L equals 2, then m sub L can only be -1 to -2 to +2. And when L equals 2, then it's going to be a d orbital. It's a 4d orbital. And so applying the parameters they give us here, 4, 2, 2 plus 1/2, that's the magnetic spin, and 4, 2, -2, -1/2. So that corresponds to 2 electrons in a d orbital. In the last example, they say n equals 3, L equals 3, and m sub L equals 0. Now, when n equals 3, L can be anything from 0 to 2, and m sub L can go from -2 to +2. But they say n equals 3, L equals 3, so this is impossible. You cannot have L equals 3 when n equals 3. The highest L can be is 2, so this is not a possible quantum state. And that wraps up your mock test.